So this is John Light, his fourth session with us. I've hosted the other three sessions and on YouTube, and this will be our fourth. So thank you, John, for giving this continued introduction, and I will turn things over to you.
Okay. Well, today we were going to talk a little bit about kind of model development. There was some talk that some of you there might have some models you wanted to share. I don't know if that's still the case or not. Anybody? No, apparently not yet. Anyway, in light of that, though, I'd like to ask you all for a little bit of feedback here in terms of what you'd like me to talk about next. I mean, basically, I've finished talking about the essential structure of these models, and
so John, I can jump in here for a second.
Sure, please do.
Sure. In terms of where we ended up, and yeah. So one of the things that we thought would be really helpful is to maybe just take us through the friendship variable, kind of see the data that you have already generated, and then compare that with the advice network, which you kind of just looked at, as well as loan. And we can just kind of look at those three.
Okay.
And that would be extremely helpful to see if we see any differences that could be useful as we try to understand these three social kind of networks or relationships.
I think I can do that. Let's see here. Yes. Okay. So what you're looking at here, I'm going to make that a little bigger again so that everybody can see it. There. That should be pretty easy. This is a sequence of models, starting with a very simple one. And I'll kind of show you how I went about adding to it and the conclusions I'm drawing, and you know, kind of basically what I think I know and what I don't know. All right. Remember that with these models, it's a good idea to use a forward selection kind of a procedure because of the fact that being an iterative algorithm, and that means that there is no formula for the final result, as you would have like in a simple maximum likelihood estimation situation where you form the likelihood function and you calculate it and just use calculus to find out the values of the parameter vector when it's maximized. So you have to use like a hill climbing algorithm that's sliding around on the parameter in the parameter space. Imagine a multi-dimensional surface, if you will, which in 3 dimensions would be, well, 2 dimensions, let's say, with, you have 2 parameters and then you have a likelihood function that's a bunch of hills, and you want to find the highest hill in that parameter space. So that's what it's trying to do. And so you want to start out with a model that's simple, but not so simple as to be completely uninformative. And usually what I will do is, when I'm dealing with a social network, which usually has a set of fairly predictable characteristics, and which moreover I've looked at using stochastic actor modeling quite a bit, I will start out with something like this specification right here. So you see you've got a rate parameter, which basically is just going to be controlling how many changes the simulations that are iterated to calculate the parameter values, how many changes are being simulated in each interwave period, of which there are 5, right? 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. Total of 5 there. Out degree is usually an important parameter to include because it basically estimates the general tendency for relationships um, to exist in your network, and also to change from one way to another. Reciprocity, and we've talked about that, is the tendency to for relationships to involve mutual choices. So I choose you as a friend, you choose me as a friend, or else that there is no choice by either of us. Both of those types of dyads are consistent with a reciprocity effect. And so basically, you know, I don't think I mentioned this before, but the idea there would be that you're likely to see a reciprocity effect in cases where the number of reciprocated ties is higher than what you might expect by chance alone. Okay, so if it were just you know, a matter of random choices, you would only have a sort of the chances for a tie forming, a reciprocated tie forming between two individuals would be basically proportional to the number of ties in the network as a whole, right? But if it's higher than that, then you start to have evidence for a unique effect associated with reciprocity. And the model will detect that and will calculate a parameter associated with that effect accordingly. Same thing with transitive triplets. This is a very typical, as I mentioned before, kind of a proximity effect often. Two individuals are brought into contact by their friendship with a third individual, and that makes them more likely, if you have a transitivity effect, that makes those two individuals more likely to become friends as well. And the 3 cycles effect, you know, which is just what you think, it's A to B to C to A. A relative undercount of triads like that suggests that the relationships tend to be A to B and B to C, but can be interpreted, and often are interpreted, as C being a lower status individual. A being a lower status individual. So basically, selection goes up the status hierarchy, would be the idea. And people are more likely to be chosen if they're higher in status, and more likely to be choosers if they're lower in status. Think of a business or corporation or any other kind of hierarchical organization where the higher ups are more sought after by the lower downs than vice versa, because they have, you know, prestige and resources and things of that nature. So in that sense, we think of that as being a hierarchical effect. And those are the only 4 substantive effects that I have in this model. You'll notice we do have an equation for the recovery factor here, but it's only predicted by shape. Okay, so that's basically just telling us something about the shape of the what you might call preference function for recovery. How does it, what is its shape relative to its own value? So if you have, and what you often see here is a situation where you have a linear shape that is positive, but a quadratic shape that's negative, which means that the preference surface is convex, basically. And it means that there is a kind of a generally preferred or canonical level of recovery factor in the population. And that may in turn shift as a function of covariance, but we don't have any covariance in there right now. Okay, so, but you include this anyway because usually, well, if you were having problems doing an estimation, you might redo the model without this equation at all, the rate recovery function, recovery factor function, because you might want to get a better idea of what these parameters are first and plug those in before you add this other stuff. But if you're going to do that, you cannot include the recovery factor as an endogenous variable in the data object, because if it's included in the data object that goes into the model will automatically add these effects here. I suppose you could include it in the model and manually remove these effects if you wanted to, but it's probably easier to just make a data object without RF in it. Try some models and then add it in effect adding another equation. And I think I mentioned this before, but in general, every endogenous variable that you put into the data object represents an equation, quote unquote. That's a value that's being predicted within the model. Okay, so bear that in mind as you do your model development. You typically do not include, like, what I'm really looking for here is I want a model that ideally includes friendship, advice, loaning, and probably the recovery factor, 4 equations altogether. But that's a pretty complicated model, and there could be a lot of interactions there. And I don't think I really want to start out with something, well, I probably am not going to get to something that complicated for a while until I feel like I've got as much learned about the individual dependent variables as I feel like I can learn without embedding them in a more complicated system. Okay, so far so good. So this is a simple model where we start, and it's going to go ahead and do the analysis, blah, 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 blah. And it comes down here. And here we have, as we saw before, the information on convergence. It's not real good, meaning that the model is probably underspecified or maybe misspecified too. But let's go ahead and take a look at the results of the parameters. By the way, it's not too surprising to see a not very good converging model at first, because you quite often leave out stuff that's very important to the evolution of the network and or the behavior. And so because the predictors you have in there are not especially powerful ones necessarily, it's going to be hard for the algorithm to find a really good hill to climb, a really nice sharp peak on that hill. It's more likely to find surfaces, the surface is more likely to have a bunch of little rises here and there, and it doesn't give the algorithm a lot of real sharp information to work with. So that's okay, it's not a good situation in the long run, but it hopefully can be dealt with as we make the model more realistic, which would be the hope. Okay, but in any case, just looking at the results here, I think we looked at this last time. We see that we have if we divide the effect by its standard error here, we get a sort of a pseudo t-statistic here. I should add there is no proof, by the way, that this is actually distributed like a standard normal variate. But there is simulation evidence that usually it approximates such a distribution pretty well. So right now that's mathematically the best we can do there. All right. In any case, we see that there is a significant, that is to say the T ratio here would be more than 2, let's say roughly, 1.96 being the standard cutoff, or 0.05. We've got a positive out degree, which is interesting, suggesting that there is a tendency for a lot of friendships to form based on the definition that we use here. We talked about that before. It's kind of a loose definition, really just one of, yeah, I get along with this guy or this gal. Reciprocity, however, is also statistically significant. So there is a tendency for one person who says they get along well with another person to, have that sentiment returned. That's not unexpected. Transitivity also appears to be common here. Again, this ratio here is on the order of about 2.5. So that suggests that transitivity effects are being found in here. And then finally, the 3-cycle effect is negative, as we expect, if we were thinking that we'd be seeing hierarchy. And hierarchy, again, remember, is the chains of A chooses B, B chooses C, but C doesn't choose A, suggesting that the status hierarchy goes from lower to higher. So A is lower status than B, lower status than C. C is receiving more choices and giving fewer, as you might expect in a hierarchical situation. I think that last finding is kind of especially interesting here, in as much as some of the research that we've done suggests a pretty flat status structure. And this doesn't really contradict that, but it still shows that there is some kind of a, what might be called, it suggests there might be some kind of a hierarchy here in terms of prestige or desirability or what have you, and that would be a good thing for us to try to look for explanations of. For example, you'd start right away thinking, well, you know, the people who have more recovery, say their recovery factor scores are higher, maybe they're higher status, or maybe people who have been living in the house for a longer time, maybe they're higher status. And if that's the case, then that would suggest that we should include those variables as potential predictors of tie formation. And that maybe if we did include those, that it would have a tendency to reduce or at least qualify that the 3-cycle effect. Okay. Questions so far?
So John, you have, this is the number 2 estimation results, and it says that there's 2,377 iteration steps.
Yeah.
So at what point do you say, okay, I'm sort of satisfied with what it looks like?
Well, that's a good question, but there's no simple answer to that. We're getting ahead of ourselves a little bit, but I will just foreshadow this by saying that a model which tells you something that you think is interesting, that's pretty subjective, right? Has pretty good sound p-values based on the, you know, this ratio of parameter to standard error. For hopefully for all of the parameters that you are interested in, either as primary substantive predictors or as control variables, those should all be hopefully statistically significant. Or if you drop them out of the model, it doesn't really affect things. And convergence should be good, better than this in particular. And there are also some measures of fit. And these are not quite like the usual measures of fit with, let's say, a regression model or something where you have something like an R-squared or what have you. But rather, the idea is that the model should predict certain kinds of overall network characteristics relatively accurately. In other words, the idea is that the micro effects in the model affect the kind of topological structure of the network. And there are some tests there that check to see how well that happens. And those are called goodness of fit measures, you know, not surprisingly. And we can probably take a look at some of those today. I don't know if we can actually run them because they take a while. They, like everything else in R-Siena, are iteratively calculated because they rely on model predictions. So you have to run a bunch of predictions in order to get them. But maybe we can try some a little bit here. So those are the criteria. Other than that, it's the same as with any other model. You know, you try to understand what's going on. And when you think you've gotten to a point where your understanding is better than it was before, and you feel reasonably confident that the results you're seeing reflect the actual data in some understandable way, right? So it's not, you've sort of eliminated the possibility that it's like weird outliers or data problems or other things like that. In other words, all the standard things that we have to worry about when we do statistical modeling. then we're kind of ready to, draw some conclusions, however tentatively, write a paper, give a talk, whatever it might be. So no magic there, Lenny. No magic. It's a judgment call, like it always is. I hope that makes sense to everybody. I'm sure any and all of you who have done actual, modeling of real world data understand what I'm talking about. And if I could see your heads, they'd probably be nodding.
Yeah, makes sense, John.
Okay. I saw Mike giggling over there in the corner. Yeah, he totally understands. Oh, dear. Mike, did you ever teach a class in modeling where, somebody would ask a question like that? Like, how do you know the model's right?
Yeah, it's hard. And a lot of times I just hope that like Andy Gelman talks about all the branching paths that you can go down when you start analyzing data.
Yep.
Mostly what I'm shooting for is that I hope that if someone were to think like me, they'd come up with the same results. But if they don't, they're going to go down a different branch, and then it's like sometimes the data doesn't discriminate between a lot of different choices. And that's just the way it is.
Yeah, and on the other hand, I mean, that's a really good point to raise. It's it also explains part of the reason why I like to cast a rather wide net early on. I mean, I'm really acting a little bit like an estimation algorithm myself, in the sense that I don't want to zero in too quickly on what I think is the optimal parameter vector, because I don't really know. I mean, I'm not sure really what the landscape looks like. And I want to get an idea what the landscape looks like before I start to bore into a particular direction. So that's always the thing. Do you go wide first, or do you go deep first? And my own prejudice is to always go wide first as best I can. Because that way, if I see something that looks interesting, I'll have an idea as to whether it does or does not conflict with some perhaps somewhat more vague result that I saw earlier on in some other part of the analysis, or whether it's consistent with it. So it gives me, in other words, some kind of a logical framework within which to make decisions about what might be going on. But it's as much art as it is anything else. I mean, of course, the old saying is, art versus science, but, science has a lot of art in it. Any scientist will tell you that, no matter what field they're in. And sometimes a good intuition is as important as, anything more technical. So how do you educate your intuition? I think you just tromp around in the data and get really dirty. And, after you've done that for a while, you have an idea about what it might and might not be able to tell you. And Mike, I think we've learned a lot about what this data set might or might not be able to tell us in the course of the last year and a half of analysis. So, that's all, it all is cumulative. Okay, moving ahead. All right, in this model, I added the amount of time the person was in residence. I think we talked about this last time, so I won't dwell on this for very long. Here we still have a not very convergent model. In fact, it's even a little worse than the last one. We are not seeing any significant effect of the amount of time that the person chosen was in residence. So people who are, how long you've been in residence doesn't seem to affect the way other people feel about you as potential friends very much. On the other hand, people who have been in residence longer seem to have more friendship ties overall than people who don't, which figures because they've had a longer opportunity to form friendships. But that seems like conditional on this, kind of iffy convergence, that seems like a pretty strong effect. T-value would be, 39 divided by 8, which is almost 5. So, and then I also, just for fun, added the in-residence variable here to see whether the change in the recovery factor might in some way be a function of how long you've been there. And Mike, this was an effort to begin looking at what you had found, which was that people who had been in residence for a shorter time tended to have steeper increases in their recovery factor than people who had been there for a while. Presumably the latter had kind of already had their improvement period and it was behind them. And there is some weak evidence of that. The parameter is positive. But no, actually, sorry, it's the other way around. The longer you've been in residence, the more increase in your recovery factor, which is counter to what your data found, but the effect is not even close to statistically significant, so I wouldn't really be inclined to interpret that as being meaningful in any particular way. But it's not even in the direction we were expecting, much less being statistically significant. That still, to me, that still doesn't mean that the amount of time that you've been in residence is irrelevant to your recovery factor. I think it just may be more contingent on some other things. And what we're going to have to do is qualify this effect a little bit as we go ahead and see if we can get an idea as to whether it's operative in some subpopulations or not.
John, your time periods are based on study waves, right?
Mm-hmm.
Because in the growth curve analyses, I'm using the resident wave. So I'm starting everybody from their first survey as if that's time 1 for everybody.
Right.
So we're marking time a little bit differently, but I don't know how that would impact the analyses.
Well, my thought about that, and I'd be delighted to get your comments on this, Mike, is that if I include the amount of time that the person was in residence at their first wave, hopefully that will take account of any differences in absolute or relative changes in the recovery factor, or in any contingencies, depending on how we fold that into interactions and stuff like that, or other contingencies associated with their choices of friends, just to look at both of those. I mean, think about it this way. If everybody was new at wave 1, then your analysis and my analysis would be identical, right? So what's different about it? Well, the different waves have different mixes of people with different amounts of time in the house, and that just means that the evidence from one wave to another is always a mix of those different starting points. But if the different starting points have consequences that we can tease out in and of themselves, the rest of the effects should still be apparent, one would think. It's just that you would have to deal with these by including interaction effects with, for example, the amount of time the person was in residence at their first wave. And we don't have any of those interaction effects here. We just have main effects so far. So the model, to do that properly, it seems to me, is going to have to be more complicated. And, it's a matter of, we're just going to have to see whether the data is strong enough and there's enough of it so that we can estimate models of that complexity reliably.
And this effect that you got there where it says effect from RS dot in res L,
Right.
is that like an effect that affects each of the period rates?
It's not a rate effect. The rate effects are separate. But what that tells you is based upon the person's level of in res L at time t0, okay? Are they more likely to be up one step or down one step, or about at the same step place in terms of the recovery factor in the next period? And it pools that information across all 5 pairs of waves, right? So it's like an average over all of those 5 pairs. So if you saw that there was a tendency for people who, let's say, have less time in residence, okay, to increase be more likely to have a higher recovery factor the next time around, then this effect should be negative and significant, right? Because the two are inversely related, just as with ordinary regression. Except that the thing that's being predicted is a probability of an upward change, if we want to think about it that way. Make sense?
So that's the estimated coefficient is related to the probability of
Correct.
upward change.
Exactly.
And what the rates are those? Is that related to an upward change too?
No, that's just related to the amount of change in the recovery factor from one wave to another. So that value, if you let me just do a quick calculation here. So what that's saying, roughly speaking, is that you have a latent tendency at each point that the recovery factor can change. Over the course of a wave, you can expect about 4.2 changes, roughly.
4.2 changes in.
Yeah,
per,
not very many in recovery factor.
Is that on compared to the people, like 4.2
yeah.
individuals?
Yeah.
Or so about 4 people are going to change on the recovery factor in between each wave.
Mm-hmm.
Oh, that's interesting.
Yeah, I know. Yeah, it's not that many.
Is that specific to individuals, or could it just be 4.2 total changes? Like potentially one person has 3.
I believe that that's the case for over the whole population. So it's not really very many. I should double check on that, by the way, because the way that these effects calibrate into your data is not completely straightforward. So I don't really have great confidence that what I just said is absolutely true. And why don't I just send around an email about that after we're done here? I just have to go look it up again, is all. But so that's just I mean, it sounds a little low to me, to tell you the truth. But that's the best I can do off the top of my head, though. But I'll try to clarify that. Very good question, though.
There was something in chapter 13 of the R-Siena manual as far as interpreting these effects, these coefficients, that get to that question. I think that one might be an individual, at the individual level, and then if you scale the coefficient by something like the range of values, I think it was like 5 to 1 or something like that, then it's some sort of average effect. I might be misremembering it, but
I would have to go look again. But yeah, that
there
sounds.
appears to be a way to get at sort of the effect for an individual versus just some overall average effect. And I think it had something to do with scaling the coefficient, but I don't remember off the top of my head.
Right. But what I can say with some confidence is that the rate functions or the rate parameters are proportional to the total amount of change in the network. In, you know, up here it would be in the network ties, and down here it would be in the recovery factor, taken as an ordinal variable. Oh, by the way, that's another thing too, Mike. I mean, you can, in your models, you can treat the recovery factor as a quantitative variable, but here I have to treat it as ordinal with rather a small number of categories. So there probably would be less apparent change in this way of calibrating it in a model like this than it would be for a more ordinary regression, even a multi-level type of regression model. But let me just, I just made a note to check that out, and I'll just send a clarifying email out when we get done, okay? But yes, there is a place in the manual where they talk about, you know, interpretation of effects and what that all means. And there's also a couple of articles that I can refer you to, which talk about it as well. Okay, chugging along here. Okay, there's a model that didn't work at all. That one had added sex to the INRES-L. That was a really dumb idea because after all, sex is something that has to be the same, you know, within a house. I mean, you within the whole data set. I mean, you can never choose anybody of, you know, a different sex because the houses are all the same sex. So including that in the network model was probably not a very bright idea. But, you know, sometimes I don't really think too clearly. Let's see, what about the next one?
The price, when it takes a couple hours for a model to run, though, that imposes a heavy penalty. But I've paid
stupidity really has a higher price with this kind of model.
I've paid a lot of those penalties myself. So
yeah, well, you know, but yeah, the longer the model takes to run, the more seared into your brain it should be. You see, I'm at the point though where, you know, being older, you know, there isn't that much brain to sear anything into. So I still tend to forget despite the heavy penalty. Oh well, what are you gonna do? All right, so here's a model which, let's see what we included in this case. Well, I included a sex ego effect because what that would do is it would tell us if there was a different tendency for males versus females to choose a lot of friends, right? If this effect were positive, it would say that females who have a value of 1 versus 0 for males are more likely to select relatively more, well, they select relatively more people as friends than men do. And if it was negative, it would be the other way around. And I still have my INRES variables here. And now I have sex, because I wanted to see if there were sex differences in the change scores for men and women. And I also have the INRES variable for recovery factor. And we have, lo and behold, a much better convergent model. So remember I said that part of the problem with really primitive models is that they can sometimes, they're just so far from being really helpfully predictive of what's going on that the estimation algorithm can only get a rough idea of what the parameters ought to be. And in fact, it might not even be sensible. The reason that I thought that in this case, the rough idea was kind of okay was because most of the findings that we were seeing in the earlier in earlier models made some sense, you know, based on what we know about friendship networks generally. I mean, there was the positive out degree effect, which, however, could be understood by the fact that, you know, you've got a relatively small number of people living in very close proximity to each other. And so the chances of the network being highly sparse, which is what we tend to see in larger, more diffuse friendship networks, like in, you know, school kids or formal organizations or what have you, is much less likely to be operative. So that made sense. And the other effects, you know, the reciprocity, transitivity, and 3 cycles were all typical for friendship networks. So I was feeling that even though the convergence wasn't great, that we were still okay. All right. And in this case, indeed, we see that the overall maximum convergence ratio is below 0.2, which is considered to be a kind of a rule of thumb cutoff. And we see that most of these so-called pseudo T ratios here are small, meaning that you don't have big deviations between successive estimations. And that means that the convergence of the algorithm is relatively good. And here are the actual results. Well, we still see the same out. Look at this. This is interesting here. The out degree effect is there, but it's less significant. That's pretty cool because an out degree effect is not, it's just telling us like how many friends do the people tend to choose. It doesn't tell us anything about why. So if we put effects into the model that start to predict why, that should take away from the out degree effect, right? Because presumably they're more explanatory of why the effect exists or why the network tie exists or why it doesn't. So that's a good thing right there. We see the reciprocity effect is about the same as it was before. It's around 3 or something. Maybe it's a little stronger. I can't remember. Transitive triplets effect is also pretty strong, but maybe a little less strong than it was before. These are good things because what we would like, we would like to see these more generic, you know, network tendency effects, if you will. We would like to see them explained net of these more generic effects by predictors that are more substantively meaningful. Then we really start to think we're getting somewhere. You know, it's a little bit like, you know, sort of a normal, say like a growth model, to have very clear evidence that such and such a variable is increasing in time over the course of your study. Well, that's great, you know, but that's not really what you want to know. So if time is your predictor, okay, cool. You know, you need to include that as a possibility. Maybe there's just a secular trend of some kind that you can't really capture, but that's the problem. You can't really capture it. What you want to know is whether the slope is predictable from something. Well, this is an analogous kind of a situation where we're not really talking about just some kind of a simple amount of change of some measured variable in time, but rather we're talking about the probability of ties forming or not forming or dissolving over time. But the substantive issue is the same. If you can have more specific effects related to your covariates, and that those tend to replace the more generic effects of just what the trend looks like from typical endogenous, often structurally oriented network effects, you're in better shape. You know more. All right. So once again, 3 cycles, significant. There is a slight tendency for males to be less likely to extend friendship ties. In effect, this rs.sex ego here can be thought of as being a sub-effect of out degree. Because out degree talks about making selections in general, the rs.sex.ego effect is saying if ego is male or female, 0 or 1, right? Excuse me, female or male, 0 or 1. Let's get that coding right there. Does that have an effect on their tendency to make out choices? Just the sheer number of them. And the answer is yes, but it's not significant. Okay, so there's a trend tendency for, we'll say a directional tendency for males to be less likely to select others as friends, net of everything else, but it's not significant. So probably this doesn't mean anything, but we'll kind of keep it in the back of our mind in case later on in a more contingent model, we see that there actually is an effect. Similar now, we have in res L alter and ego effects. There is no alter effect. That is to say, if somebody has been in the house for a long time or not a long time, they're not any more or less likely to be chosen as a friend. So an alter effect has to do with the characteristics of somebody being chosen and how that affects the likelihood of a tie incoming to them, okay? And we can see here that this is close to 0. You know, the t-value there would be, you know, less than 1, much less than 1, but a half. So we can say that apparently the amount of time you've been in the house doesn't affect how attractive you are as a friend. Okay. But interestingly enough, the amount of time that you've been in the house does affect how likely you are to make friendship choices. We saw this before. The only thing we can say now is that it's true even when we control for stuff like the sex of the chooser and all these other factors here. So there's still a tendency from, as we saw from the previous model, for people who have been in the house for a long time to make more out choices of friends.
John, if the alter effect had been positive and significant, would that suggest that the newcomers are being targeted by existing residents? Like people are actively reaching out to them and saying, yeah, come on, let's be friends. I'll help you through
It might. Of course, you don't know where those, the thing is, you don't know the ego characteristics from which that's coming from. So that's not really directly evidence of that. All it means is that, all that would mean would be that the longer you'd been in the house, the more likely you would be to be the target of a friendship choice.
No, I meant the other way around though. Like the shorter
if it's negative, then the shorter time you'd been in the house, the more likely you would have been to be targeted as a friend.
So if a negative alter effect went with a positive ego effect, would that,
yeah,
that'd be a nice, that combination would kind of suggest that the long timers are picking out the newcomers and befriending them.
Yep, and you could confirm that by having these effects and then a multiplicative interaction effect. Because then you could be sure, you know, that that particular combination is really what is going on in the data. Exactly the same as you would with an ordinary regression model. Cool? So yeah, exactly, you got it, man. All right. All right, let's stop for a second. How are we doing? Is this edifying or boring or?
No, very helpful, John. It's very useful to look through the program.
Okay. So I don't need to make it more exciting by, you know, singing or dancing or playing the bagpipes or anything?
That would be entertaining, but
I don't know how to play the bagpipes, by the way.
But I'm getting a lot out of it. I'm going to have to rewatch this again to like make sure that I didn't miss any of the points. But thank you for putting it out there, John.
Yeah, I know there's a lot going on here, and I want to encourage everybody to read and reread some of the literature. You know, things in the manual about points you don't quite understand. That's always a great place to start. The several articles that I think I've mentioned to you. about written by Snyder's and his colleagues about how these models work and how to interpret them. I find that when I'm trying to learn a complicated new method like this, I go back and I reread stuff, oh geez, half a dozen times maybe. And by the half a dozenth time, it's starting to feel familiar, you know? And then if I go do some analysis and read it, you know, yet again, along about the dozenth time, it's like, oh, right, okay, now I really got this. So there's a real, I don't know, there's a real, for me, a real process of just constant attention to it that makes it start to make sense. So if you still feel like it's a little slippery and you're not quite understanding how everything fits together and stuff like that, don't feel bad. It's the nature of the beast.
Yeah,
I mean,
I've looked for shortcuts, but there are none. There's only one way to do it, and it's repetitive. That's the only way I found to work.
Right. Phil, well, you're a mathematician, you know how exactly how that works in terms of learning a new area of math, right? You know, you sort of start out with getting the definitions, and then you look at some of the theorems and start to understand what's connected to what, and then you start to work with it. And it takes a while before your intuition starts to really kick in and you understand the way the whole system works.
Yeah, exactly. It's and often in that process, it can feel like you're beating your head against the wall.
Always does. I don't know, for me, it always does. There's always a point there like, why am I doing this? You know, why don't I just go sell fish or something? You know,
Yeah.
but those of us who have made it this far usually manage to persist for some psychotic reason. I have no idea why. Okay, let's see if this model adds anything to the program. No. Actually, yes. This is kind of interesting here. And I'm vaguely remembering that I might have gone through this last week, but if that's the case, you know, forgive me, it's still worth mentioning that we have a significant and negative effect of sex on recovery factor. What this is saying is that women, because you know, 0 is male and 1 is female, it says men have a tendency to improve their recovery factors at a greater rate than women do in these houses. That's interesting, but you know, one wants to be careful in over-interpreting it. It could mean that you know, the women are in better shape when they come into the house, for example. We haven't looked at that. We'd have to interact sex with the recovery factor score in order to see that. So that would be the sort of thing we'd want to see next. Notice once again, we don't have a significant effect of in-res even when we control for sex. I was thinking maybe we would, but no, it doesn't matter. But anyway, that is something to keep in the back of our minds, the fact that we have a sharper, for whatever reasons, we seem to have a sharper increase in the recovery factor for men compared to women. All right. Here I just trimmed the model a little bit so it doesn't really add anything and the results are still about the same. By trimming, I mean I took out some of the really insignificant effects because they just use up degrees of freedom without adding anything. Okay, here we have a model that fit better. Now this one's interesting here. The network part of the model is the same. I haven't really changed anything there, and we see all of the effects here are about the same as they were. But what I did is I added a so-called average alter effect to the behavior dynamics. What I wanted to see was is there a tendency for people who have as friends, people who are more recovered, are they any more likely to increase their recovery? And the answer to that question is yes, they are. You can see here that this average alter effect is positive, 0.34, and you've got a standard error there of around 0.19. So it's not quite 0.05 significant, but it's probably around 0.08. Let's just see what that ratio actually is. Let's see, I said, I'll say 3413 divided by 1878. Got 1.82. I mean, yeah, that's going to be around 0.7, something like that. So that's pretty good evidence, especially in a preliminary model. So that's something, that is probably the first really interesting substantive finding that we have here. We are seeing that if you affiliate with people who are more recovered, you are more likely to improve your own recovery. I believe I reported this finding to you guys several weeks ago, and it remains one of the more interesting results that we have so far, suggesting that, and raising the question as to, okay, fine, what does it take then to for you to select another person who's more recovered as a friend? What differentiates people who do that from people who don't? So looking at this from the standpoint of ego, the chooser, you know, what is it about that person that makes him or her want to choose a more recovered person for a friend, or feel comfortable doing it? You know, whatever verbiage you want to use there, because we're not sure about the motivation, right? We just know that they do it. It could be a characteristic of ego that makes them attracted to such people or not. Maybe they're really interested in, you know, having a recovery, and they want to particularly focus on people that they see as having more recovery wisdom, recovery capital, if you will, and try to become friends with those people. Or maybe they find such people more attractive, would be perhaps another way to say the same thing. Whatever those people have going for them makes them attractive to certain other individuals with less recovery capital, but why? That's the question. So that's really the thing that I think, one of the big questions now that we want to focus on here is that. Let me see here.
John, do we get the same relationship when we looked at the other network? Like, for example, loan and advice seeking, do we get the same finding?
I'm going to take a look at that in a second. In fact, why don't we actually go over there? I'm going to just take a quick look through these and see if there's anything else I wanted to mention to you. Oh, okay. Actually, this one's worth looking at. Because remember I said that we need to know, you know, what is it that makes people want to pick a more recovered person as a friend? Well, one of the first things I wanted to check was to see whether there was a similarity effect. That is to say, am I more likely to choose you if my recovery level is about the same as yours? Because if the answer to that question is yes, it would kind of say something to the effect that, well, your recovery, you have to find a way to recover, to get your recovery up to a certain level before other more recovered people, before you're able to form friendships with other more recovered people, okay? So you have an influence effect here from the average alter, but it's one that has qualifications, so to speak. And you've got to do some other preliminary work on your own, which we would then need to think about what that was. Or the alternative would be if, let's say, there was a negative similarity effect, or people who are high in recovery are likely to pick people who are low in recovery, or vice versa, then that would suggest that the dynamic is one of the better off helping the worse off. Well, unfortunately, if that was your hypothesis, there's no evidence for that. There's a trend or directionally positive relationship. That is to say, for people who have similar recovery to choose each other as friends, although it's not significant. But it's definitely not negative and significant. So there is, at least without further qualification, we can say that there's not a general tendency across all houses, all different types of people, all everything, for dissimilarly recovered people to choose each other as friends. And that's interesting because we have had some indications that there was some kind of a dynamic like that going on in the houses. You know, I want to go back and look at the analysis that Nate and I did last year. We wrote that paper about this having to do with quality of life. But quality of life was a qualifier. Quality of life, as you know, is a component of the recovery factor. But there's other components. And one might argue that this particular effect that we're finding here is that we're using a measure that's broader, that's more all-encompassing. And apparently, when you look at things in that way, you don't really get as strong of a you know, the rich helping the poor kind of an effect. At least, as I say, without further qualification, interactions with other characteristics and so on. So anyway, I thought that deserved some mention because that's substantively pretty important. All right, there's more things I could say about the friendship network, but let me go on and let's look at the loan results. Would that be okay?
John,
Wait a second, you know what? We're out of time.
how about if we pick up on the loan results on Friday? How does that sound?
Yeah, that's what we'll do.
That'd be great. Friday,
That's what we'll do.
1 o'clock. We'll continue. And also, if anybody has further things that they're working on, we can bring up questions, have a chance to, I know Phil said he had some questions, so we can maybe have a little time to just throw some questions at you too.
Yeah, and you know, look, and in the interim, feel free to send me emails or whatever with questions, and we can discuss stuff. There's all that too.
Fantastic.
So you don't just have to suffer.
Yeah. I mean, that's all I'll probably do, Lenny, is I'll just fire a couple quick emails to John about RHNet and JML utility. Please. As far as like working with that on the Mac. So
feel free.
Yeah, that's something we could do offline easily, John.
Sounds good. All right. Any final thoughts, questions, anything before we go?
I think that's it. Sounds good. And yeah, we'll catch up with you on Friday, and we'll keep pushing this along.
Okay.
Great.
Sounds great, guys.
Okay.
Thanks for your attention. See you Friday.
Thanks, John.
Thanks, John. Appreciate it.
Oh, my pleasure. Bye-bye.
Myra? Oh, Myra's gone.
I'm here.
Yeah, I'm going to have to take off here, Lenny and Ted. I'll touch base with you on Friday for the meeting.
That sounds good, Phil. And if you're having any connection problems or things like that, let us know, and we'll keep working to try to get you connected up.
Okay, sounds good. So 1 o'clock Friday?
Yeah, sounds good. Okay.
Awesome.
If I have any questions, Phil, I'll reach out to you too. I feel like you might know some of the stuff that I don't.
Okay, yeah, that's great, Ted.
Appreciate your help, man.
Okay, no problem. Take care, guys.
Yep, bye.
So Ted, why don't we give you like a half hour till like 12:30 or 1 o'clock, and then we can reconvene if that sounds good. Just give you.
Yeah. Do you want to ask Myra if she's coming back, and then we could do 1 o'clock?
You know, I'm going to see if they're available at 1 o'clock, but if not, we can still meet at 1. How does that sound?
Yeah, I'm good. I'm going to go eat lunch real fast, and then I'll be back at 1.
Okay, sounds good. Bye-bye.
All right. Thanks, Lenny. Bye.